Okay, so now we're going to take a look at electric potential energy of point charges, because this is our next step towards understanding electric potential. Now, the reason we want to look at potential energy for point charges is because, like was mentioned in the last video, conservative forces are easier to deal with when using energy because it's a scalar quantity, which basically means we don't have to consider which way forces are pointing whenever trying to solve a problem. Now, as a quick review, we have delta U is equal to the potential energy at point B, or the final position, minus the potential energy at point A, which is the initial position. And we can also represent that as minus the integral from A to B of f dot ds, which is the same thing as the negative of the work done. Just to show you how this is done with an example you should have seen already, we're going to look at the change in gravitational potential energy in the universal sense using universal gravitation, not the near-Earth approximation. So we have delta UG is equal to the negative of the integral from point A to point B of f of g dot dr, which is the negative of the integral from our initial to our final. So this would be like the surface of the Earth to maybe some other location. And universal gravitation is minus g m1 m2 over r squared dr. And so when you do that integral, we get minus g m1 m2 over r evaluated from our initial to our final. Now remember that this negative here cancels with this negative here, but when you integrate this function, you get an additional negative sign, and that's where this one comes from. Okay, so let's take a look at developing our expression for electric potential energy. So delta UE is equal to the negative of the integral from A to B of the electric force dot ds. So delta UE is equal to the negative of the integral from A to B of, now the electric force for a point charge is Coulomb's law, which is K Q1 Q2 over r squared times dr. And when you do that integral, you get K Q1 Q2 over r, and then we have to evaluate that from A to B. So then we get delta UE is equal to KQQ over B minus KQQ over A. And I want to point something out here real quick, and that is that this is U final minus U initial, and that this whole expression here was the negative of the work, and all I'm really trying to call to your attention is we're bringing it back to our original relationship between work and change in potential energy, and that was that delta U is equal to the negative of the work done. We're just representing it with different letters. That's all we're doing, with different variables. Okay, so when you want to calculate the energy of a particle, then you can use this expression here, everything that we've done here with Coulomb's law, and you end up with this expression, or you could expand it out into what we have here. But typically what happens is that we take the initial position to be infinitely far away. And if we take the initial position to be infinitely far away, that makes this whole expression go to 0, that whole term. And we end up with delta UE is just equal to K Q Q over B, which is our final position. Now, what is our final position? Well, our final position is how far we are from the source charge. So when we look at this expression, this is just Coulomb's constant right here, but this capital Q I'm using as the source charge, and this little q, or Q2, is the test charge. And so this B is the distance between the source and the test charge. Okay, now you don't have to look at it as source charge and test charge, but I think it's probably easiest. And so what we have is Q here and little q out here, and the distance between these two is B. And this little q here came from infinitely far away. And the reason we do that is because when you're infinitely far away, no energy exists. So what is the point out of all of this? Well, we have delta UE is equal to K QQ over B, and delta U, now this doesn't appear to be a delta, and oftentimes we write this as the energy of the charge. Okay, so this is really just written as UE is equal to KQQ over R, where R is the distance between the two charges. But this is only valid when you're coming from infinitely far away. It's only going to be valid for point charges. And if you choose, you can just use the expression delta UE is equal to minus the integral from a to b of KQQ over R squared dr. Okay, so you do not have to use this UE is equal to KQQ over R. You may choose to do the calculus yourself, and that's completely valid. So now that we have a basis for determining the energy in a point charge, the electric potential energy of a point charge, let's look at how we do this for a system of charges. And this is something that you should have seen last year, and hopefully you still remember it from last year. Okay, so when you have a system of charges and you're looking for the energy of that system of charges, then basically you have to find the energy for each individual charge and add them all up. And that's what I'm showing you here. I've drawn this, or I've written this expression for 3 terms, but if you had 4, you could just as easily add U4, and if you had 5, you could just as easily add U5. Okay, but typically you're only going to be working with 2 or 3 charges, and we're going to just stick to that. So I'm not going to be using 4 and 5 here. And these charges, I'm going to place these charges in a line. And I'm just going to say that they're all positive charges just for simplicity's sake right now. And the process for determining the energy of the system is to just first look at each of the individual charges. So when you place the first charge, if I call this charge 1 and this is charge 2 and the third one is charge 3, then placing the first charge is done energy free. Now, the reason that there is no energy involved in placing the first charge is because there are no forces acting on that charge. I am referring to electric forces which are acting on that charge. And if there's no electric forces acting on the charge, then there's no way there's any electric potential energy as a result. Now, the second charge has an interaction due to the first charge only. Now, since the second charge is only feeling a force due to the first charge, we can say that U2 is equal to K Q1 Q2 over R12. Okay, so R12 is this distance right here. And R13 is this distance. And R23 is going to be this distance. And here we have U1 is just equal to 0. All right, now finally we have the third charge. When the third charge is brought into this, it not only feels a force due to charge 2, but it also feels a force due to charge 1. You must include the energy that is due to each of those interactions. So U3 becomes U of the first charge acting on 3 plus the U of the second charge acting on 3, which is going to be K Q1 Q3 over R13 plus K Q2 Q3 over R23. And so finally, when you want to get the total force, or U of the system, U of the system is going to be equal to U1 plus U2 plus U3, which is equal to 0 plus KQ1 Q2 over R12 plus both of these terms right here. I'm not going to be able to squeeze that in. I'll do it on the next line down. So our final answer is U of the system is equal to all of that. The charges do not need to be in a line. Okay, so there's a couple of rules here. The charges can be in any arrangement. The second thing that is important to keep in mind is that like charges, they're going to create a positive delta U, and unlike charges create a negative delta U. Now, the reason for this, I think, is pretty simple to see. If you have a positive charge here, and you're bringing a positive charge from out here, then there's an external force pushing forward, but there's a repulsive force pushing backwards. And it's that repulsive force, the electric force, which is the force that's doing the work for our energy. That's the, it's the electric force is what's going to store or take away the potential energy. So the electric force is backwards, the displacement is forwards, and so we end up with potential energy being added to this particle. Now, if this were negative and this were negative, we would still have the same repulsive force. But if we had this situation where we have a positive charge and a negative charge, now there's an attractive force between the two, and the displacement is also forward. So the work is positive for this scenario, which means we end up with a negative change in potential energy. So you just got to keep that in mind. Like charges create a positive change in potential energy, unlike charges create a negative change in potential energy.